In this video, we will be discussing the formulas and names for various types of compounds, and specifically dealing with ionic compounds. The formulas for ionic compounds are generally comprised of positively charged ions or cations and negatively charged ions, which are anions, and the formulas are always written so that the positively charged ion comes first, and then there may be some subscript indicating the number of those ions. Following that comes the negatively charged ions, the anions, and the corresponding number indicating the number of the anions. If there's no number, it's implied that that number of ions is 1. For an example, we can think about an ionic compound comprised of calcium ions and chloride ions. In this case, the calcium would be generally a 2+ ion. That's the only ion of calcium. And chloride is -1. This then would form a formula that it would have 1 calcium and 2 chlorides, so as shown here. So this is the lowest whole number ratio for this particular combination of ions. In general, the cations that are found in ionic compounds are often metals of some sort, although there are some examples of nonmetals that come together to form positively charged ions. And likewise, the nonmetals tend to form negatively charged ions, anions. There are certain cases where the positively charged ion or negatively charged ion is a group of atoms. This are referred to as polyatomic ions. And in some cases, there may be more than one possible charge associated with the ion. Ionic compounds are generally comprised of both the positively charged ions and the negatively charged ions, and in some cases these may be polyatomic ions, as shown here, the example of the ammonium ion being a positively charged cation. In some cases, you want to be able to name that ionic compound, so you would always go about naming the cation first, and then you would name the anion. So, for example, if you have something like NaCl, the cation which comes first in the formula would simply be named by naming the element, which is in this case sodium, and then we would name the anion, which in this case we use the root of the element's name. So chlorine has a root of chlor, and then we end that with the "ide" suffix, which indicates that it's negatively charged. Ionic compounds generally are polymeric materials in the solid state that have a three-dimensional regular repeating pattern of positive and negatively charged ions. So therefore we generally write the formulas as the lowest whole number ratio associated with the ions. This would be the so-called formula unit. Some examples of this: for sodium chloride, the formula would be NaCl, whereas for iron 3 sulfate, it requires 2 of the irons and 3 of the polyatomic ion sulfate to produce this lowest whole number ratio of atoms. And in the last example, cobalt 2 permanganate, there would be 1 cobalt and 2 of the so-called permanganates, which are MnO4, within the parentheses there. The crucial thing is that the overall charge in combining the positive and negatively charged ions has to end up being 0, and therefore we have to come up with a way to mathematically deal with that. As an example, if we take a relatively simple compound like strontium fluoride, having the formula SRF2, and we recognize that there's one of the cations, one of the strontium metal cations, and two of the fluoride anions, and then multiply by the charge of each of the ions. So the cation strontium is 2+, whereas the fluoride is -1. We would end up then having 2 positive charges and 2 negative charges as a result of that. And we add that together, and of course you end up with a net charge of 0. As an example of how to come up with the formulas for ionic compounds, we want to look at the ionic compound that would result between the reaction of magnesium metal with nitrogen. In this case, the magnesium will form a 2+ ion, whereas the nitrogen will form a 3- ion. Our goal now is to find some combination of these two ions that, when added together, result in the formation of 0 net charge. To do that, we will need a number that both 3 and 2 can divide into, and that turns out to be 6. So we will need a total of 6 positives and 6 negative charges. So, in this particular case, if we take 3 times the 2+ from the magnesium ion, that would give a total of 6 positives. And if we take 2 times the 3- from the nitrogen anion, that would give us a total of 6 negatives. Adding those together results in 0 net charge. Therefore, if we then think of this in terms of what's often called the crisscross approach, we recognize that the number associated with the particular ion becomes the subscript for the opposite ion. So, for example, the 2+ becomes the subscript 2 for the nitrogen, and the 3- becomes the subscript for the magnesium ion. As another example of an ionic compound, in this case, if we take and react aluminum metal with phosphorus, we will result in the formation of aluminum phosphide. In the case of aluminum, the common ion is 3+, whereas for phosphorus, the common negative ion is 3-. The combination here is such that if we use the crisscross approach, we would come up with a formula which would be Al3P3. But it turns out this is not the lowest whole number ratio, which is what is required to write the formula for ionic compounds. So what we have to recognize then is that both 3 for the aluminum and 3 for the phosphorus can be reduced down to a lower whole number ratio, which in this case is aluminum phosphide with the no subscripts, because it is implied that those subscripts are 1. So, if we have 1 aluminum 3+, which is then giving a total of 3 positives, and 1 phosphide, which is 3-, we have a total of 3 negatives. Add those together, we end up having 0 net charge. At this point, we will need to discuss a little bit about how to go about naming various ionic compounds. This is given the term nomenclature. A nome is the Latin word for name, and so this is a systematic way of going about naming things. Generally, we're going to be naming what are referred to as inorganic compounds. Inorganic systems generally don't contain carbon, although there are some examples. Usually, if there is both carbon and hydrogen in the formula, it would be referred to as an organic compound. These compounds have their own naming system, which is somewhat different than the inorganic systems. There are examples of carbon-containing compounds that are considered inorganic, and generally these are things that are carbon where there's no hydrogen directly bonded to the carbon. As we had pointed out previously, ionic compounds are generally comprised of a positively charged ion, which are usually metals, and negatively charged ions, which are usually nonmetals. In the case of the so-called monoatomic ions comprised of a single atom, generally we can make some good predictions about the charge of those ions based upon where they are in the periodic table. So it turns out that if we are in group 1A of the periodic table, these are often known as the alkali metals. The only positive ions for those elements are +1. If we are in group 2A, these are the alkaline earth elements. They are generally 2+ as far as the charge of their ions. And then we have over in group 3A, these are 3+ ions. Thallium happens to also have a +1 ion. And so we can make some pretty good predictive power from those positions in the periodic table. The negative ions, the so-called group 7A or halide elements, are 1-. In this case, we put hydrogen over the top of that, but hydrogen can also be 1+. If we go to the group 6A, these are generally 2- ions, and group 5A are 3- ions. In those cases, we are gaining electrons, and so therefore negatively charged, and an attempt to have the same number of electrons as the noble gas. In this case, we want to consider why do the ions form the particular charges that we observe, and so we can take a look at some electron configurations and look for some sort of pattern associated with that. So for example, we can take a look at removing electrons from various subshells, and that can help us understand why the ions that are formed are stable. So, as an example, tin, which is in group 4A, it has an electron configuration where the core is krypton. We have a closed subshell, the 4D is completely filled. And then we have the valence shell, which is shown in red here, which is 5s2, 5p2. If we were to remove all of the valence electrons from a tin atom, we would then form an electron configuration which is very stable, a krypton 4d10 configuration, and this would end up being a 4+ ion. This is probably the most stable ion for tin. In addition to that, if we only remove 2 electrons, we would have a situation that would have a configuration of 4d10 5s2, where both the D and the S subshells are full, and this is also relatively stable. The transition metals and the ions that they form are a little bit more complex because of the potential very close energetic interaction between the S subshells and the D subshells. So it turns out that generally the transition metals form multiple positively charged ions, and some of them are more stable than others. In the case of vanadium, the vanadium metal would have an electron configuration with 5 valence electrons, having an argon 3d3 4s2 configuration. If we remove some electrons from initially the 4s subshell, we would form a 2+ ion, which is relatively stable, and would have the 3 remaining electrons in the D subshell. It turns out that therefore we could